Radical Dude here, and today I want to talk to you about geometric progressions. Now, what I just did there was an arithmetic progression, walking down those stairs. But a geometric progression is when you take any number and you multiply it by what's called a common ratio, and you just keep multiplying it each time and writing down that answer. So you take a number, multiply it by a common ratio, get an answer, then put a comma, multiply by a common ratio, get an answer. And that whole thing is a geometric progression or a geometric sequence. So I'm going to demonstrate with this basketball. Come on over here. Little do they know that when in my playing days, I used to be called Radical Raspberry. That's where I would make my moves and the fans would blow raspberries. Now, what we're going to do with this geometric progression is I'm going to show you how to do it with a bouncing ball, and then we'll do that. So, using a bouncing ball, I'm going to demonstrate what a geometric progression is. So, for example, I take the height of the ball, let's just say it's 4 feet, I'm making this up, right? And let's just say it obtains 80% of its bounce. So you start at 4 feet, it should bounce back up 80% of that, which is 0.8 times 4 feet is 3.2 feet. And then you multiply that number by 0.8 and you get 2.5. And then you multiply that by 0.8 and you get 2.0 something. Those numbers that you list are called a geometric sequence. You list the number 4, and then you go to 3.2, and then you go to 2.56, etc. And if you put them together, you add them up, that's the series. Okay? That's how the geometric series works. That will be for an episode on logarithms. So,
Action.
So if we list each height of the bounce, that's the sequence. Each entry is the term in the sequence. And if you add them all up, that's like a series. That's called the geometric series. It's kind of like a World Series, right? You have each game individually, that's the sequence, and then you put it together and you got the series. Go Yanks. Now I'm going to show you the mathematics behind it. Come on. Come on. Okay. If a ball retains 80% of its height after each bounce, how much has it fallen after 5 bounces, starting at 100 feet? Okay, I'm going to do this problem 2 ways. One, I'm going to do it where we can see it exactly, and then the other is I'm going to use the formula that we just proved on geometric series. So, I like to visualize things. So just say I have this ball, I throw the ball, and it bounces, boing, and it goes up. Before we do that, so here's the ball right here, and we throw it 100 feet. So this is 100 feet down. Put it as straight down, but if I draw the line straight up and down, you're not going to see the bounces as clearly. So it goes down, and here comes bounce 1. Bounce 1. Doing. Now it goes up 80%. So how high would it be? Is it's now at 80 feet. So we don't care how high it goes up now. We're just counting how much it has fallen. So it falls 80 feet. Then it hits bounce 2. How much is it going up now? It's going up 80% of 80. So you multiply 0.80 times 80, and you're going to get 64, which means that it is now going to fall 64 feet. And it comes down and it bounces 3. So now you're going 80% of 64, which when you use the calculator, it means it goes 51.2 feet. Now we have bounce 4. Now it's going up 80% of 51. 80% of 51 is 40.96. And now here comes bounce 5. And the bounce is coming from the height down, up. So I don't even care, because look at this, 100 feet bounce, and then it stops. So we added that 100 from the bounce. 80 bounce, 64 bounce, 51 bounce, 40 bounce. So these are our 5 numbers. So you just add these up. You add up these 5 numbers, and you're going to get a total of 336.16 feet. This is how much the ball has fallen in total, just counting what it has fallen. Now, another way is to use the formula we had just proven, which would make this one actually faster, is you start with the A, which is the 100, 1 minus, the ratio is you're multiplying by 80, 0.80, so it's 0.80. And now you're taking that, oops, I shouldn't have put the parenthesis there. You're taking it to the 5th power. So it's 0.80 to the 5th power. You do that first, then the 1 minus. And over here we have 1 minus r, which is 0.80. So I could just do part of this in my head. This I can't do in my head. 80 times 80 times 80 times 80 times 80. This is 0.20. And when you work this all out on the calculator, you are going to get the same answer, 336.16. And that's it. What if you wanted the total amount? As it just keeps bouncing, it gets smaller and smaller and smaller and smaller. Well, then your n would approach infinity. And as n approaches infinity, your summation would be a times 1. This whole thing, 1 minus r to the n, as long as r is between 1 and negative 1, this whole thing will just stay as 1 divided by 1 minus r. Oops, 1 minus r. But I'll do that for another video. Okay, so we're going to prove this geometric series formula. S sub n equals a times the quantity 1 minus r to the n divided by 1 minus r. And I've listed here what each letter means. A is the first term, R is the common ratio, N is the number of terms, and S sub n is the summation of n terms. So let's take a look at what it is and what we have. So what you have when you have a geometric series, which is the sum of the sequence, it runs in this form. A times r to the 0 plus a times r to the 1 plus a times r to the 2. And it keeps going on and on and on until you get to a times r to the n minus 1. N minus 1. Now, why is that? So let's just say I have a sequence, for example, that goes from 64, right, to 32, to 16, etc. And 64 is the first term, and each time to get to 32, I've taken half of 64. And to get 16, I've taken half of 64. And then the next term would be 8, and that is half of 64. And then for the 64, I didn't even take half. So your A would be the 64. The ratio is a half. Now, why do I do it to the 0? Because the 64 is really 64. Yo. Let's see how that pen works. It's really 64 times 1/2 to the 0 power. That's where this A times r to the 0 is, because you're not affecting the first term. Then the second term of 32 is r to the first power, which is the r1. Then you're doing a half times 64 is the same thing as a half squared. That's where the r squared comes. And then if you wanted to get 8, it would be a half times a half times a half times 64, which is r to the third. And that would be the next term in this thing. So far we have that. Now, what I want to try to do is I can create a pattern where I can get rid of some of these things just by multiplying. The quickest way to do it is by multiplying the whole thing times r. So if I multiply r times s of n, I'm going to get, let me erase this real quick. I shouldn't say real quick because I am not that good at this technology. Let's try to erase. There we go. Okay. So if I multiply by r to the Sn, then I have r times ar to the 0 plus r times ar to the first plus r times ar to the second, all the way down to r times ar to the n minus 1. Now, if we simplify these, you're going to see that r times r to the 0, you just add the exponents. So I have ar. And then here, I'm going to have r times r is r squared. So I have ar squared, and then ar to the third. And then it continues all the way until r times r to the n minus 1. Well, this is a hidden 1, right? So you add, and 1 plus n minus 1 is n. So I have ar to the n. Now, if I look at this, which is r s sub n, I'll rewrite it again here, r s sub n, and I look at just s sub n, they repeat after ar to the 0. Ar to the 1, ar to the 2 is the exact same thing here, right? Ar to the 1, ar to the 2. So if I were to subtract, look what happens. So I take S of n, the top line, minus RS of n. And look what I have. I have AR to the 0, which is just really A. And then AR to the 1, this cancels with this, and this cancel, right? When I keep subtracting, I get to 0. And I come down to AR to the n minus 1, right? Minus, now what happens to AR to the n? Well, right before this AR to the n, guess what it is? It's AR to the n minus 1, because it's 1 unit less than the AR to the n, and we're counting right up. So this goes 1, 2, 3. So this is 1 less than the n. So this cancels with this, and since I'm subtracting, I'm left with a minus AR to the n. So far, so good. Now here, I can factor out an s to the n, and I'm left with 1 minus r. And over here, r to the 0 is 1, so I'm left with a, and they both have an a, right? They both have an a, so I could factor out an a, and I'm left with, this is 1 minus r to the n. I'm almost done. All I have to do is divide by 1 minus r, and I have the formula. That's it. And I just proved this formula. Thank you. All right. Well, this has been Radical Dude, and I hope I was able to teach you something. And the Dodgers should never have left Brooklyn.